Hello again, everybody, and welcome to another Geo-Institute live stream. It is not Tuesday or Thursday, and so you're probably wondering, what the heck are these guys doing going live on a Friday afternoon? That seems very silly. Let me assure you, it is nothing but the most serious business over here at the Geo-Institute. We have gone live today on Friday at 2 p.m. because it is March 14th, 3.14, aka Pi Day. My name is Brad Keeler. I'm the director of the Geo-Institute, and we're about to have one of our most fun live streams of the year. Few administrative things. If you don't know anything about the Geo-Institute, after you watch this today, head over to geoinstitute.org, and there you're going to find out so many things about us, including that we're a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. After you're done watching this today, while you can do this while you're watching, I guess. If you like what you see, click like, subscribe, get notifications, and we'll let you know every time we post something to the YouTube channel. That is a very important message. Two other things. The Ralph Peck bobbleheads are coming. If you have your Terzaghi already and you have been waiting anxiously for a Ralph Peck one, or even if you don't have a Terzaghi and you've been waiting for the Ralph Peck ones, now is the time. While you're at geoinstitute.org, click on Student Participation Fund in the top right corner, make your gift of $96 or more to student programs. And as long as you're in the US or Canada, in your mailbox will arrive a Ralph Peck bobblehead. We have a gazillion other things you can choose from as well for other donation levels. So you will want to do that. Now, I did mention it's Pi Day. We did not totally ignore the day other than this live stream. I'd like to share with you something that we did a little bit earlier. We were down in the cafeteria here at the ASCE World Headquarters in Virginia, and we celebrated with some pie. We had a cherry pie, we had a pumpkin pie, we had a quiche over there on the right, and some pie-shaped Jell-O up there in that mold that's up in the top right. Of course, what would be Pi Day without some math and some geotechnical engineering? I know you've all thought that. So we brought in one of the experts. What I like to do every year is find a GI member who is well-versed in math, well-versed in geotech, and can meld the two together for a really cool presentation. And from the University of Texas at Austin, where I believe it's what happens there changes the world? Or what starts there changes the world?
What starts here changes the world.
What starts there changes the world. Shout out Ellen Rathje on that one. We've brought to you Krishna Kumar, faculty member at UT Austin. He's going to do a presentation today, a little bit on Pi, and then he's going to talk about machine learning and AI. If you have any questions for Krishna, put them in the chat box to the right of the window where you're watching this, and we will get to those at the end of the presentation. Krishna, this is your time to shine. Thank you for doing this, for being here and being fired up about Pi Day.
Yeah, thank you, Brad, and thank you so much for having me. Really great privilege to do this on Pi Day and show all the interesting aspects of AI, math in geotech. And I wanted to start off with this wonderful example of counting pi. And this is one of my favorites because you can see pi not just in circles, but also when you do experiments like these in the 1700s. This was by French scientist Buffon, who started throwing needles randomly. And whenever it cuts across the line, he counts the number of needles thrown versus number of needles that sticks on the line. And if you divide that, you basically get an estimate of pi. And that's always fascinating when pi kind of appears out of nowhere, but whenever there's pi, there's always circles, and there's a lot of interesting math behind it. So today on 3.14, we want to talk about the aspects of AI in geotechnical engineering. And it's been a really buzzword out there for the last year or 2 years since OpenAI came out with ChatGPT. I want to talk a little bit more about what other AI methods are there, how can we use it, leverage it, and also, of course, talk about large language models. So first, I want to disambiguate what AI, machine learning, and deep learning are, so it gives us an understanding of what they mean. The big question I get asked is, do we have artificial general intelligence yet? Or do we have Skynet yet? From the Terminator, we are pretty close. It is very good at thinking. It's very good at reasoning models, but I don't think it is sentient. I don't think it will become sentient, but it is going to be really, really useful in evolving us and the engineering field. So whenever we talk about artificial intelligence, that's the general big term that we use to talk about being able to solve complex level problems at a human level. Machine learning is going to be a subset, and this is where most of engineering AI application comes in, is using machine learning. This could be like decision trees, deep neural networks, which is a deep learning method, which is used quite a lot. So although people generally use large language models like ChatGPT or GPT-4o, DeepSeek, they are a subset of AI, and large language models are not the only AI algorithms. There are many out there. I do talk about AI, but I'm going to talk about why do we not like AI. AI models are like black box models. So if you have like a bunch of parameters, something magical happens and you get really, really interesting results. But most often you're not able to explain why you got that result because it doesn't show you the inner workings, or the inner workings, even if we can understand what's happening, is extremely hard to decipher. So my interest in AI is, how do I make them explainable? How can we give physical engineering meaning to these AI models? And the other big issue I have is you mostly train it on data. This could be experimental data, simulation data. Train them, and then when you're trying to evaluate or test it in new sorts of areas, as long as you're interpolating within the training data range, then you're okay. But when you're extrapolating, so in this case, if I train it on like 0 degrees and 5 degrees, 15 degrees, and 20 degrees, tested it on 10 degrees, then this will be okay. But if I tested it on really steep slopes, like 30 degrees or 40 degrees, then the extrapolation generally fails. And because these are black box models and we don't know what the inner workings are, it's really hard to know when you're interpolating and when you're extrapolating. So it's important to understand these limitations so we can use AI models or machine learning models much more effectively. This is one of my favorite graphs because it tells you like how the different AI machine learning algorithms are in terms of how accurate they are versus how interpretable things are. So if you look on the right-hand side at the bottom, these are your general classification rules. So think about flowcharts going to the left and right. Those are general classification rules. They're less accurate in terms of data-driven models, but they are very, very interpretable. You can just follow along the flowchart and understand what's happening. As we go up higher and higher, you get more complex models like support vector machines, random forest. We'll talk about that in a moment. And neural networks, and this is where LLMs kind of go even further, where the model is extremely complex. And as the complexity increases, the interpretability kind of drops, but their accuracy goes up. So this is how the evolution of machine learning has been. Is just like the more machine learning models are becoming more and more complex and more accurate, but we are losing the interpretability. We want to be going the opposite direction. We want to have very highly accurate models which are extremely interpretable, so we don't lose hundreds of years of history of machine learning and engineering that we've acquired over a long period of time. I'm going to go through 3 different examples of machine learning in geotechnical engineering. starting off with very simple decision trees and random forest, then talk about how can we accelerate simulations, and finally end up with everyone's favorite of how large language models work and how can we use it effectively in doing engineering designs. So we're going to go to Christchurch, and this is the work of my mentor friend, Dr. Rachi at UT Austin. And what we're going to do is look at predicting lateral spreading from the gold standard data set of Christchurch, where we have like 10,000s of CPT data, and we are going to predict whether lateral spreading is going to happen or not. And whenever the horizontal displacement exceeds 0.3 meters, we're going to say it's lateral spreading. Below 0.3, there's no lateral spreading. And we are going to use not the CPT data initially, but start with just simple features. Features like how high a particular site is, what is the steepness of the slope. So like steeper the slope, the more likely it is going to lateral spread. But what is the groundwater table? The shallower the groundwater table is, the more likely lateral spreading could happen. And PGA, if you're going to assume like a high PGA means lateral spreading, low PGA less likely to cause lateral spreading. I wanted to explain this, although this seems very obvious in terms of the features, like steeper slopes would likely to run out further than flatter slopes. But we want to be able to see, can we extract these relationships back from an AI machine learning model once it learns to predict these behavior. So we're going to give these features, give a collection of data set where we have a yes or no to lateral spreading, train the model, and they've trained it on a random forest with different features, and we are also going to include CPT features in addition to those that I talked about. The L here is basically distance to the river. So if you're closer to the river, you're more likely to be saturated and have a phase to flow. Where further away from the river, less likely to happen. Okay. So we're going to start off with decision trees. These are the most simplest of the machine learning algorithms we have. It's basically a flow chart. You classify yes and no depending on different criteria. You can start off with slope angle. Say if it's steeper than 5 degrees, yes, it is likely to lateral spread. If it is less than 5 degrees, no, and so on. So distance to the river, if it is, again, closer to the river, further away. Groundwater table, if it is closer to the surface or no. We have a very, very explainable, easy to understand decision trees. The model is very interpretable, but the accuracy of these models are generally lower. So they get about 60%, 60 to 70% in terms of accuracy. What we can do to improve these decision tree is instead of using one, we end up using hundreds of decision trees. So one decision tree basically might use slope as the initial classifier. We could use distance to the river or slightly different values. And by initializing these classification nodes as parent-child nodes and use different classification, we can end up with a different number of trees. And what we want to do at the end is basically look at hundreds of trees and see what is the majority. If the majority of the trees are saying yes to lateral spreading, then we go say that's a site that's going to lateral spread. So if you ever played this game in exhibitions where you're asked to guess how many jelly beans are in a jar, that's a great example for loss of large numbers. So if you want to win in that game, what you need to do is make random guesses. Not just you yourself making a random guess of what the right number of jelly beans are, but if you could ask hundreds of your friends what they are, if their guesses are completely bonkers, from like one person saying it's 5 to another person saying 5,000, what happens is as you start adding all these numbers and taking the average, that is the loss of large numbers, the answer will eventually tend closer to the exact value. And that's the same thing that happens within single decision tree and random forest. Is like we have a weak model, but we have hundreds and hundreds of these weak models. And by aggregating the result using large loss of large numbers, we can get the accurate answer. So we're going to use random forest, train the results, and you can see this particular random forest model, almost all of them are closer to 90% accuracy. So this model is doing really well, and it is able to predict whether a particular site is experiencing lateral spreading or not. And that's great. When something as uncertain and as variable as geotech, we are able to reach 90% accuracy, that's a really important result. But my main issue is, how can I understand it? If I give you a decision tree, you will be able to plot it and look at what's happening. But if I have hundreds, if not thousands of decision trees, then it's really hard. So here I'm only visualizing a single decision tree and seeing what's happening. But this allows me to see what is happening in a single decision tree, but I'm not able to understand what happens as a whole. And we want to be able to explain what happens as a whole. And so what we do is normally end up plotting the results. Everything this is green is correct predictions, and there are some incorrect predictions. These are false positives, cases where it didn't lateral spread, but we think that it should have. And false negatives is where we missed the prediction of lateral spreading. So there are a couple of them, and a couple of them seem to be clustered around. So we want to be able to understand why this is the case. And I previously told AI models are really black box models. You won't be able to understand what's happening, but there are certain tools like Shapley values and interpretable machine learning models, which allow you to understand the contributions of different features. So let's say there are 3 employees in the company, and we want to evaluate what is the contribution of each one of them. We can look at individually what the contributions are, and we can also look at what is the contribution as they start to interact with each other. We're going to do the same thing. Instead of employees, we are going to use features like distance to the river, groundwater table, peak ground acceleration, and look at what is the interaction, how much do they contribute to every decision. And we can do this multiple times, starting with each feature, next feature, and then so on. Do these combinations, and we'll be able to evaluate what the individual contribution for each of those decisions are going to be. So we're going to go look at that. So this is an explanation of a particular site. So one site where that particular site is very close to the river. The distance to the river, L, is pretty low, reasonably high PGA, groundwater table is close to the surface, and anything that is red and moving to the right, about a value of 0, means it is positive for lateral spreading, and anything blue and moving to the left means it's having a negative influence, or saying there's less likely chance of lateral spreading because of this feature. And what we see here is, like, let's say if we had 100 decision trees, almost 90% of them, or 90 of them, are saying this particular side is likely to lateral spread. And we can see why, because this is close to the river, high PGA, and shallow groundwater depth. That makes sense. And if you look at a case where there was no lateral spreading, this site has a very deep groundwater depth, almost 3 meters, further away from the river. And all of these are positive indications of why a particular site did not experience lateral spreading. And this is important. You're not just saying like there's a 90% chance this site is lateral spreading. You're explaining from an engineering principles why this is happening. And this is what I like about interpretability and not just using a black box AI model, is it allows us to understand the underlying workings of these models. And of course, we can also figure out when it starts to learn things incorrectly. So in this case, it says that there is only 8% of chance that this particular site is lateral spreading. And the other side where it's saying 53% of lateral spreading. But if you look at here, there is a huge movement in negative direction. This is saying there's no chance of lateral spreading. And if you look at why, it's because of a PGA. And this PGA is 0.54 G. And that's a really high PGA. And this model is predicting no lateral spreading because of high PGA, and a positive effect of lateral spreading because of a low PGA. So if we do that in classes, that basically means something's wrong. Like our predictions or our engineering understanding is that whenever we have really high acceleration, there's more chances for things to move. So if you plot this in a data plot, where if you're plotting the shaft values, positive shape values means lateral spreading, negative shape values means no lateral spreading, and PGA is the amount of shaking we're giving the ground motion. You can see for really high PGAs, there is no lateral spreading. This is coming from the data, and this is why explaining models are important, because in this case, all the high PGAs were in this really rocky region, which did not experience liquefaction, and it ended up learning that whenever there is a high PGA, there is less chance for this particular site to liquefy. So by adding explanations, we are not only making the AI models useful, but keeping all our engineering tradition and understanding and enhancing our engineering judgment using AI models with explainability. So want to shift to another applications of AI, which is accelerating numerical methods. We know a lot of us do finite element simulations, finite difference, and I want to show some really cool applications where AI can actually make things go faster. So I mainly work on landslides, so my interest in being able to simulate really large-scale simulations. So on the left is a numerical method called material point method, which is really useful to do large deformation modeling. And it takes a while to run these problems. This takes about 3 hours to run in the barrier example, but I'm now showing you a machine learning model, which is on the right-hand side. It's not just predicting the final result, but it is actually doing the entire simulation. So given an initial configuration, you can build machine learning models which allow you to replicate an entire simulation. So to see enough simulations for it to learn what the local interaction is. And the benefit is it does that in about 5 seconds. Of course, I cheat and not tell you what the training time is, which is now 2 days, but and takes about 20 simulations for it to look and learn from it. But once it learns, we can change the configuration. We can change the geometry, material properties, loading conditions, and all of those will run in few seconds. The reason why we are able to do it is instead of using what is called a multi-layer perceptron, which is a traditional deep neural network, where you want to learn the entire system dynamics, and if you want to learn it for like 10,000 or 100,000 nodes or particles, this becomes extremely expensive. Instead of learning the whole system dynamics, what we try to learn with a graph neural network is map out the entire domain using nodes and edges in a graph. So just think of as discrete particles or a collection of particles, and trying to learn the local interaction. If you've ever done discrete element methods or molecular dynamics, this is like the particle-particle contact. Or if you're familiar with finite elements, just think of it as an element, and the constitutive law is what we are trying to learn in this edge-edge interaction. By learning this local interaction, what it allows us to do is basically learn from the simulation. So I need about 20 simulations, learn from looking at the simulation, discretize the domain into graph, learn how individual nodes act. So like what is the stress, what is the mass of the particle, what is the velocity, and learn that interaction. And the interaction in this case is distance between two particles, the relative stiffness between each other. And that way we are able to predict the entire dynamics of the system. If you want to check out, our codes are publicly available, so you can check it out on GeoElements/GNS. And coming from a numerical methods background, whenever we want to do some physical constraints, we can add physics into machine learning models. There is an area called physics-informed neural networks, which adds physics as a PDE constraint loss, or in this case where we know like we want to conserve momentum, we can make sure the edge messages are conserving each other. So particle I exerting a force on particle J is going to be the same as particle J exerting on I, but in the negative direction. So we can enforce these conservation of mass, conservation of momentum, and be able to develop models which can generalize really well. So in this case, I want to say that we did 3D graph neural network simulations, which trained it on like only one barrier, and we were able to extrapolate it into barriers where we had more than a single one. So we have 5 barriers, and it's able to learn and predict what that behavior would look like. And that's really interesting because now you're able to go beyond what the training data set is. And I've previously said like extrapolating outside the training data regime is one of the difficulties of machine learning models, and we are able to do that really well. We are able to trained it only on an aspect ratio of 1, that is the height to the width is 1, and then able to predict what happens under different geometries and different friction angle. Of course, if you go like way outside of that friction angle, this is going to fail, but it does a reasonably good job at this point. What this means is we can do really large-scale landslide studies. So this is one of our asynchronous distributed landslide simulation, which we did it with NPM and GNS, where NPM allows you to do this 50 million point simulation, but we are doing it in close to real time. So GNS helps us accelerate this. So I can show you a real-time video of what's happening. And you can see that this is an exaggeration of what happened in the OSO simulation case. And we were going for a dramatic effect of what was happening in the OSO landslide. Right. So far I've been talking about forward models, that is run your simulation, like take it forward in time. So you're doing, given an input, run your graph neural network simulation and get your results. A lot of our geotechnical analysis involves doing inverse analysis. So we know the result and we want to calculate either the material properties or we want to be able to calculate what the initial configuration was. So this is called the inverse problem, back analysis, and so on. Normally what we do is called as finite difference. So start with an initial geometry or material property, change it a little bit, look at what the results are, and we can find out what is the change in result with respect to change in input parameters. For that, you have to do 2. If you want to do a simple finite difference, it means like run it, change the initial configuration a little bit, get the result, and then you can calculate what is the gradient of your result with respect to the input. Instead of doing that, what we are trying to propose is called automatic differentiation, which is the approach machine learning runs on. And in machine learning, this is called backpropagation, which allows you to not only calculate the result, but also get the gradient accurately in a single shot. We're going to do a very simple problem. We're going to calculate what is y as x1 squared plus x2. Assuming x1 is 2, x2 is 3, we square this, we get 7. So what we do is lay it out in a computational graph, put in x1, x2, what happens to x2 as squared it, add it, and get the results. So nothing fancy, put your results, push it through a flowchart, you get what the forward pass looks like. This is just a problem setup because we want to be able to do the reverse mode, which is the backpropagation in machine learning, is calculate the gradient of your result. This could be a runout, this could be your displacement, strains, and then you want to calculate what is the force or material property. We want to be able to calculate the gradient of each node with respect to the next one. So we do this on each edge, and you can pre-compute it because edges are already well defined, and this is basically your computational graph. And then if I want to get the gradient of your result with respect to the input, all I do is chain rule. And here, if I do that, you can see that my gradient is exact, unlike finite difference where the gradient will have like a small error. Automatic differentiation or algorithmic differentiation means I get exact gradients. So this means now we can draw an optimization problem, back analysis. This is us using graph neural networks with one of our student, Youngjun Choi, who graduated from UT, who did optimizing barrier location using GNS. We are trying to configure how these barriers are going to be placed so that it limits how far the runout is going to happen. And remember, each one of these simulation only takes about 5 seconds. We can run through a design problem in a matter of minutes and not have to wait significantly long for our finite element or NPM simulations to run. And you can see how we go from our initial guess to our final profile or final configuration in a matter of minutes. We need to remember this is a machine learning model. There is an inherent error in it. There is an approximation that we do. So the GNS is the red dot, and the blue, which you see here, is the actual NPM result. So I'm not saying replace all your numerical methods with our existing approaches, but instead we get you pretty close to your answer in a matter of minutes. So machine learning models are significantly useful in accelerating numerical methods. Final thing I want to touch up on is like ChatGPT or LLMs. Large language models has been a buzz since 2023 when GPT came out. But I wanted to start with explaining how GPT actually works. So GPT or any language model is basically a text prediction engine, meaning it has read thousands and thousands, if not millions of books, and it is able to predict what is the next sequence of words. All the results I'm showing here are actual outputs from LLM models. And what we do sometimes is open up the hood and show you what's happening underneath. And here I have a very simple question that I asked GPT and asked it, I have a dry collapsible site in arid Arizona. Complete the sentence. So if you think about it, like my favorite example is like if a cat sat on a fill in the blank, I would normally say mat because I've seen so much text where it says cat sat on a mat. And the same thing happens here to GPT is it has seen enough text. It says dry collapsible site is not suitable for construction. And here in these cards, you can see it has a list of probable words, probable set of tokens for each prediction. And it always picks the most likely token. And the reason why it always picks the most likely token is because we have set a temperature, which is the creativity setting, to all the way to 0. When you do this, it allows you to keep the setting be deterministic. So if I ask this question every single time, it is going to give me exact same output each time. That's okay for engineering purposes, but if you want it to be a language model and want it interactive, write poems with it, then you want it to be creative. That's where you dial up the temperature all the way to 1. ChatGPT has a setting of about 0.7. It means instead of picking the most likely word, it ends up picking something less likely to happen. In this case, it's now saying the dry site is saturated with water, which went downhill because this is what we mean by hallucination. The language model is coming up with something really crazy, and it is not right. And that's mostly because our temperature setting is asking it to be creative, meaning deviate from everything it has seen. And this is not a really good thing for engineering. And we want to always keep the temperature setting to be close to 0 as possible to have at least deterministic answers. Even the answers are wrong, I want it to be consistently wrong. And everyone's question is my language model or our language models, our AI models going to replace us? And you can ask this. This was GPT 3.5, so it's a slightly older example where we asked it to do a simple bearing capacity design for Leaning Tower of Pisa. And it ended up giving a result of 6,000 meganewtons. It got the formula wrong for bearing capacity. And on pi day, if you have clay soil, undrained condition, that's another case where pi comes up as 5.14 or 2 plus pi. Seeing this issue with LLM is kind of sad because it didn't understand the formula correctly. And it also thinks gamma times D is density of the clay layer, and ends up estimating 6,000 meganewtons is the load. The actual load for that particular case is 98 meganewtons when we had only 3 stories. So we got this result completely wrong. Even a factor of safety of 3 is not going to save us. So what can we do? What we can do is, instead of asking LLMs to do calculation, we have tools which we already built, like calculators, bearing capacity tools. Instead, we can build something called an agentic LLM. Agentic LLMs are LLMs that does a workflow where it goes through an action, observation, and a thought. It's going to do an action. It's going to observe what the results it got. And then based on the result, it is going to think about what is the next set of action it needs to do. So by building these tools, we can go ahead and ask exactly the same question. Now, this is the entire exchange or internal workings of a LLM. This is what we would call as chain of thought reasoning. And you can see here, initially it says, oh, I need to do bearing capacity design. Can I have a soil investigation report? So when I give it the soil investigation report, it identifies where the clay layer was, extract the bearing capacity, undrained shear strength, and then realize it's the leaning tower. So it's a circular foundation, use the appropriate factor of safety, end up doing the bearing capacity, and then it does the 2-to-1 stress transfer because the clay layer is 5 meters below the surface, and then got the exact load as 98 meganewtons. So in this case, your LLM model is not just giving you the final result, it actually shows you how it ended up getting to that result. And what this means is we can do a lot more calculations very effectively, have reasoning abilities in AI models, so we can do things much more complex. The final example I wanted to show today of what LLMs could potentially do is writing a geotechnical report. So what we're going to do is give it 10 9-board logs and ask it to do a geotechnical investigation report for a 9,000 square foot building with parking areas. Gave it to a language model, in this case Claude, which is developed by Anthropic. It read through the 9 reports, and it thinks it basically names every single soil it has seen in those 9 reports. It's not very useful. It's saying like, these are the soil types I've seen. And then it thinks that there is a lot of soft surface soil that needs to be excavated. It's not very specific how deep the excavation should be. What is the recommendation? It does say like shallow spread foundation is useful, but it doesn't go into the details. And the rest is just generic, not very useful information. This is where when OpenAI came out with O1 model, kind of changed how large language models were working. So I've previously shown you a single chain of thought reasoning when we did the foundation design. And I've also shown you a temperature setting. So we can change the temperature setting to change how it goes through that chain of thought. Instead of doing a single chain of thought, we're going to do lots and lots of chain of thoughts. We're talking like 5 to 10 chain of thought, and then learn or use a reinforcement learning algorithm to basically improve this training. So we are asking it to learn how to solve problems. Instead of asking it to learn about knowledge, we are now teaching it what are the steps it needs to do in order to get to the solution. And what we do is have a verifier that basically confirms whether or not it got the solution. So it basically say, yeah, if you follow these steps, you get to a solution. If you don't follow this step, then you're getting some mistakes. So by doing it repeatedly, the LLM models or the reasoning RL, reinforcement learning based models, are now able to come up with reasoning of how to solve these problems. So again, now we are using OpenAI's O1 model. It's just not a reasoning model. And we built reinforcement learning on top of it. Now we asked it to read soil reports, and we know how to write soil reports. So it starts to think about things. So it's able to look at the reports. There are 9 borings. There are uncontrolled fill at the top soil, about 1 to 3 feet depth. So it's able to identify information, then it is able to make judgments like it is not suitable and it needs to be excavated. Then we asked it to write a report. This is a reasoning model, and now you can see how well it does. So here you can see that it did the reasoning, wrote a geotechnical consideration section of the report where it says the boring encountered uncontrolled fill, the top 1 to 3 feet. That needs to be excavated within the building area and replaced with uncontrolled engineering fill. It even names some of the ASTM standards of like what to replace it with. And if you look at the report, which is an actual geotech report written by a professional geotechnical engineering firm, you can see it's almost exactly the same. Both recommending removing the uncontrolled fill in the 1 to 3 feet, both recommending a spread foundation, whereas here we also go and say how to replace or what specific engineering fill it needs to do to replace it. So LLMs are coming a long way to doing geotechnical considerations, writing reports, doing analysis for us. And the important thing to remember is we need to be able to explain why it made these decisions. And that's a very, very important thing, not to lose hundreds of years of geotechnical engineering or engineering and physics that we have learned over the years, and keep that in-house. I want to show how the future would look like. Maybe someday we can just walk into a site, take a video, or even in this case, write a text saying like, generate me a building. This particular part where you go from text to an image is DALL-E, and then the next pipeline is from us, where we use what is called as a Gaussian splat to go from images to 3D. And then we are able to directly import it into a simulator. So this is an undergrad student doing this work where you can just say, build me a building, apply a load and see what happens. And we can also go do the same thing with video data and be able to build rapid digital twins, be able to evaluate it in simulators which run in seconds. So there's a huge potential for AI to revolutionize geotechnical engineering. Want to pitch one of our programs, which is Chishiki AI. Chishiki means knowledge in Japanese. It's an NSF-funded Center for AI in Civil Engineering. I'm the lead PI of this. What we have is online courses on AI. So watch this space. There are free courses from NSF-funded curriculum on AI in civil engineering. We are also giving out fellowships. We just finished the second round of fellowships this year. So we support PhD students and undergraduate researchers working in AI in civil engineering. So watch the space, and hopefully you enjoy this talk. And I'll want to finish it with one of my other favorite examples of counting pi. And this is from 3 Blue 1 Brown, Grant Sanderson, who is a YouTuber, math expert. Like the Buffon's experiment where throwing needles, he found out this is like discrete element method, so which is very exciting for me to see two particles colliding on a frictionless plane. But when these two particles collide, one is about 10 power 6 times the other, the number of collisions is always converging to 3.14159. Again, that's pi, but there is somewhere a circle hiding behind the scenes. So I hope you all find you're missing our imaginary circles, or actually bake a circular pie and enjoy the Pi Day. Thank you so much.
That was pretty cool. Thank you, Krishna. I really enjoyed that. I've got a whole list of questions for you here. But I will also say for the viewers, if you've got questions for Krishna, put those in the chat box to the right of where you're watching this, and we will get to all of them as long as they're reasonable and related to today's talk. So I want to start with a little bit of high-level machine learning and AI stuff, because I think it's become one of those phrases that just gets thrown around, and even people who don't have any idea what it is have started working it into conversation, and you start hearing things like, well, AI can solve that. Well, that's very nice, but you got to know what you're doing a little bit. I want to ask first about the biggest issues that you see generally for machine learning and AI, specific. I mean, it can be specific to the geotech discipline or to civil in general.
Yeah, I think the big issue is because ChatGPT became so mainstream, it became synonymous to what AI is. And one of the things I wanted to show was LLMs are not the only AI models out there. Out there mostly for geotechnical or civil engineering purposes, like our traditional regression models are machine learning based models to graph neural networks, convolutional neural networks, and all of these machine learning algorithms which are outside of what we would normally call as LLMs. The big thing is big companies like OpenAI or Google, they're not going to build tools which are specific to civil engineering or engineering in general. And we've been learning all the physics, so it's up to us to go incorporate physics into these AI models. We need to be able to teach what are the physics laws. It can't just learn from books. We need to be manually constraining it by putting it in an equation and saying, oh, if you're doing this, you need to obey this particular partial differential equation. Like I was showing the foundation example, I took an OpenAI's model, but I gave it access to geotechnical tools. And giving it access doesn't mean like, here's tools, go do it. Instead, writing it an interface so that it is effectively able to go ahead and decide which tool to use and when to use those tools. And those are the developments where you need to know both the AI knowledge and the geotechnical knowledge to be able to do it. And it's not something we can outsource it to Microsoft or Google to be able to do that. And I think that's the big thing I want people to do is understand all the geotech knowledge they have and try to effectively incorporate it inside an AI model so it makes our life easier. It will accelerate quite a lot of work for people who understand both machine learning and AI, but it will do things very, very quickly, but very badly if you don't understand the fundamental geotech. So it's not something we can replace and say, oh, AI will do this, but we need to be building AI together for the future of both civil and geotechnical engineering.
I like that Sean McEwen, who watches a lot of these things with us, put in the chat, how about AI can help solve that instead of AI can solve that? And I think that's a good way to say it. We do have, Sean's got a question in the chat too, but I get to do one more of mine first because I'm running the show today. I wanted to ask about, I guess it's not just risk, it's more uncertainty, right? Because with any engineering problem, generally you're looking to eliminate uncertainties, but before you're looking for a solution. What uncertainties do you see AI and machine learning adding to the process that maybe we're just starting to reckon with?
Yeah, I would say there are two levels. One, the uncertainty on the data in which these machine learning models are being trained on. Sometimes we don't even put in what uncertainties are, like what equipment was used, how calibrated was it, what is the uncertainty in the measurement that the equipment made in collecting all these data, and then we just train a machine learning model on top of it. So there are methods like Bayesian neural network that allows you to propagate uncertainty, but even then you need to have some form of a distribution of uncertainty or quantification of uncertainty in the original data that was collected so you could propagate it through your model. And the other uncertainty is sometimes before we used to do regression models and people will give equation and give uncertainty bounds. Now we are giving out AI models without the equation and without uncertainty bounds. And sometimes you don't even know what weights we're trained on. So we have uncertainty in the model itself. So we've kind of gone from, I know the equation, I know where it is working, to a model where we don't know what the equation is, we don't know what the uncertainty is, and we don't know how good those models are. So there's quite a lot of work that needs to be done in terms of understanding training distributions and how can we use it in new untested regions to propagating uncertainty through these AI models.
Which I think the two emotions that I would say that conjures up for me are excitement, but also almost frustration, right? Like I think about the first simulation that I wrote in QBasic in like 1992 or whenever it was. And if you didn't have those parameters in there, you weren't going to get any results back. And I mean, a worst case, your program wasn't going to work at all. And best case, you were going to get something useless back. So as you teach this specifically, like how do you teach that, I guess? Because you don't want to box people in on one hand, but on the other hand, you're writing a program here essentially is what you're doing. Yes. How do you teach creating that box to students?
I think we are going through the same cycle, but with a slightly different field. Like we went through the cycle of numerical methods starting in the 1970s with finite element methods. And we all know like you can put in some numbers and it will give you colorful plots. But it's just that. It's a colorful plot until an engineer looks at it and understands what is actually happening and be able to verify it. And for that, we had to teach numerical methods, constitutive modeling, advanced geomechanics. And we need to be able to do the same thing by opening up the black box for machine learning models. So add interpretability, like I was showing with Shapley values. Add physics-informed constraints, like physics-informed neural networks and scientific machine learning, where you bridge both the machine learning model and the hundreds of years of numerical methods. Yeah. So you can converge to a solution where you can start believing why this model is giving me the correct response or not. In most of our applications, I use it as a really fast way to get very close to the solution. And the last step can be the numerical method taking over. So it's usually, that's like having the cake and eating it too. Is the best way to do it.
Or eating a pie.
Yeah. Yes. And in this case, our AI models is getting us pretty close to the solution, switch it to a numerical method where we can get more accurate simulation. So we still need to learn numerical methods and understand how AI works and incorporate all the physics and engineering that we learn so that it becomes more effective as a tool.
Very good. Now, here's one from the audience. This is the Sean one that I mentioned a minute ago, and this is a little bit of a scary one to a lot of people, I think. As we use AI more, will we use junior engineers less, with senior engineers reviewing the final result, or I'm adding this in, taking us the last mile, as you just said with your numerical modeling example? Eventually, there will be fewer junior engineers and soon no senior engineers. What are your thoughts on that?
I think with every new tool we get, our field evolves. I won't see it as a case where we would lose people. We would just move on to doing more and more complex and challenging problems. So like, we have a very high factor of safety. And there's like data-driven methods where you're monitoring-based methods where you're continuously monitoring. And there's only so much an engineer can do in a day. It's like giving them an ability to do, if not one simulation, now your ability to do 1,000 simulation, 10,000 data analytics, and comprehend what is all happening. So yes, you can see it either as losing junior engineers, or you can now see junior engineers using these tools and behaving like a senior engineer. So now senior engineer now needs to do a much more complex problem because their junior engineers can do what they've been doing with their experience or expertise being encoded into AI models, helping junior level engineers move up. So I see as not losing the people at the bottom, but like people at junior, senior level going higher levels and doing more complex problem, making geotechnical engineering more sustainable, less reliant, or at least reduce our factor of safety, bring in uncertainty, quantify risk, and do more challenging, more complex engineering problems.
That's great. I love having academics do these kind of presentations because you can say whatever you want and you can just pontificate, and it's a lot of fun. So thanks for fielding all these. We have a few more minutes, so if anybody has any additional questions, just pop those in the chat and we will get to those. I want to ask you now, I'm trying to prioritize the questions I have down here because like I said, I wrote down a lot. I want to ask what you think about areas of the profession that are still, I guess very visual is maybe the word I'm thinking about. And bridge inspection is one where we still have a lot of people going out on sites and you know, visually looking for damage.
Yeah.
How do you think communities like that can start to integrate? I mean, either tool, I guess, but we'll specifically say AI here.
Yes. So, in fact, we have a funded project through Federal Highway Authority, led by Salvatore Salamone at UT Austin, and I'm part of that team, where we are working on convolutional neural network models deployed on drones and head-mounted displays like HoloLens. So you could automatically map out the entire cracks and be able to estimate what is the strength of this particular bridge deck. Okay. I want to highlight an important thing here is we have convolutional neural network models that's developed from computer scientists or machine learning experts. But civil engineering kind of brings its own unique challenges, which is CS people are not going to solve. The unique challenge here is all our construction sites are either remote or with very little connectivity. And if you're thinking of deploying these machine learning models, like CNN models are used to tag people on Instagram, Facebook has huge data servers doing that. And then now you're asking a single tiny drone compared to a mile-long data center. You want to compress that model and be able to do that with very low connectivity. The network speed is not fast enough to send all the data and live stream it. So we need to develop civil engineering solutions to these machine learning algorithms. So we can't just like, okay, let's take this and put it to a civil engineering problem, but fundamentally rethink civil engineering from what will happen to civil engineering if we have machine learning? How should we design things if we are able to do this automatically? So I think it gives us a paradigm shift in how we see the world. But visually, that's one great example is inspection. The other one I kind of briefly mentioned, but didn't show, but the text to video was showing that, is go from drone videos of our construction sites and be able to build a digital twin of it. Normally our digital twin is like a BIM model, but BIM model is not real-time update. You can say 4D BIMs, but you can't have, oh, where's this truck right now? And I can just fly it around, take a full video and convert it to a full 3D model so I can compare it against BIM and see, am I behind schedule? Can I put a crane here? Is there a space? All of those decisions can be accelerated with AI, and that's exactly what us as a field need to develop these tools and not depend on CS or machine learning folks to do that, but civil engineer building these tools will fundamentally transform how we see our field and the infrastructure and the people it helps.
That's awesome. I have one final question for you today, and it's a very, very serious one, Krishna. It is Pie Day. What are your favorite pies?
Oh, my favorite is hands down chocolate pecan pie. I crave that all day long.
Is that now anything else? I mean, because I think for me, our definition of pie is very broad, right? And so we've broadened it to literally anything that has a crust and a filling. So it could be an empanada, it could be a pasty from the UK, or we eat those in the Upper Peninsula of Michigan too. Fruit pies, savory pies, like a quiche. Is there anything after the chocolate pecan for you, or is that your one and only?
My first three options are chocolate pecan pies.
I like that. I mean, and you live in the right place for that, right? That's fantastic.
Yeah, it's like I absolutely wait for that time of the year where I can have unlimited pecan pies.
Oh, that's amazing. Krishna, this was so much fun. I want to thank you again for doing this today. I always look forward to Pi Day. It's so interesting. We had a few years ago, we had Matt Evans talk about granular mechanics. We had Eric Jensen last year from University of Colorado, and people can go back and watch these on the YouTube channel. They're fantastic. I have to give a shout out, I think, to Katerina and to Ellen for recommending you to do this, because you did a great job and it was a lot of fun. And thanks for weaving everything together and giving people a lot of instruction on AI and machine learning as well. So,
yeah, thank you so much, Brad, for having me, and special shout out to Katerina and Ellen too for recommending me for Pi Day. Thank you so much.
For our viewers, if you liked what you saw, and you probably did because you're here at the end, click a like, subscribe, get notifications, and yes, we will let you know every time we post something to the YouTube channel. If you're wondering, and I'm sure you are, when our next live stream is, we're going to be back at this in just 4 days. Next Tuesday, with GeoStrata Extra. It's a special bonus episode from the February-March issue where Majid Gayoumi and Ali Farahani from the University of New Hampshire are going to be talking about, I feel like I have to do a voice when I say this, soil moisture from space. So you're going to want to tune in for that. You can sign up at Eventbrite. We also have our annual business meeting for GI coming up on the 25th on the YouTube channel, 2 p.m. And also on the 27th, a special presentation on the updates to NAVFAC DM72 on foundations and earth structures. You will not want to miss that one. These revisions have been, I think, 36 years in the making. So you are going to want to see that as well. Whew, that's a lot of stuff. Again, we're going to be back in 4 days with more stuff. Our producers today, we had to double team it, special effort, because we had some audio issues. Amber Davis and Aurora Flieger. Thanks again for being here, Krishna. Everybody out there, have a happy, festive Pi Day, and we will see you next week.